Hello everyone, welcome to the final section of Chapter 8, Acids and Bases, which will be 8.6, and we're going to talk about buffers. And you've heard us talk a little bit about them throughout the rest of the chapter, but we're going to focus on those so you know exactly what these are. Basically what a buffer does is it resists a change in pH. So if you add acid to the water, normally that pH is going to drop. In a buffered solution, though, the pH won't drop. Instead, like what they're showing you here is if you added the hydronium and it was at 7.0, it might go all the way down to a 4. If you added a base, a hydroxide, it might go all the way up to a 10.5. If you have a buffer in the solution, though, and it's at 7.0, and you add the same amount of acid, it might only go up to 6.9. Or it may only go to 7.1 if you're adding the base. So it allows you to buffer a solution, that is, it keeps it from dramatically changing if you get an acid or a base added to it. The reason they work is because you have, remember we talked about water, and in water we said it can be an acid or a base. It can be an H plus or an OH minus, or we talked about the hydronium and the OH minus. You just have to have 2 waters if you're going to write it like that. Okay, so the water can either be an acid or a base because it can either add or take away a hydrogen ion. And so in the body we have to have buffers because our blood needs to stay around 7.4 pH. So the range needs to be 7.35 to 7.45. That is very narrow. So it's very important that we have things that are going to keep that in range. So buffers allow us to do that no matter what's going on in the body to try to keep that pH in that same narrow range. The buffer solution then is going to be a combination of an acid and its conjugate base because it's going to be able to donate a hydrogen or accept the hydrogen. Okay, so a lot of times what you have is a weak acid and then the salt of its conjugate base. That's why we write it with an Na, because sodium often forms the salt of the acid. If it was HCl, for example, the salt would be NaCl. So typically you have equal concentrations of the weak acid and then you add the salt already in there. Sometimes it's a weak base and the salt of the conjugate acid. So either way, it just depends on what pH you want to keep the solution at. In the acetic acid acetate buffer, you have acetic acid and sodium acetate. Okay, so you see the only difference, just like we saw with the conjugates before, is that you have the hydrogen on one and without the hydrogen on the other. And so in order to put it in the solution, you put the salt form, because remember salts, you know, if you think about table salt, sodium chloride's a solid, right? So that's how we get the sodium acetate into the solution, is we get the salt form of it. The salt will produce acetate ions and sodium ions, right? Because it's going to dissociate. The salt is added to provide more concentration of the carbonate. So, the acetate, than the weak acid by itself. So you've got a lot of this, and so you have a lot of this. And so what that does for us is it allows you to have the acetic acid that, when added to the base, can remove the hydrogen from the acetic acid, create water and the acetate. So what that's saying is it's going to be able to, if you add more of a base to it, it can basically grab that and pull it in as water. It doesn't make sense. Hopefully it will in a minute. So basically all we're doing is we're neutralizing the effect of adding a base if we have the acetic acid. So the acetate ion neutralizes the H3O+. Going to go back for 1 second. The acetic acid can neutralize the base. The acetate can neutralize the acid and turn it back to acetic acid and water. We're doing both of those at the same time. Okay, going back again. Acetic acid takes care of the base. Acetate takes care of the acid. By having both of those in there, you're going to be able to neutralize whether you add acid or whether you add base. It takes care of both ways. And so by having the buffer in there, if you add acid, it's going to keep that pH from going lower. If you add the base, it's going to keep that pH from going higher. So this buffer system is going to allow you to maintain the pH. Now, what we say? A buffer solution is going to be the acid and the salt of the conjugate base. So which of these combinations would make a buffer solution? The first one, you've got hydrochloric acid. Its conjugate base is going to be chloride, and so potassium will make a salt of that, so that one would be. See about the rest of those. Put me on pause if you need to. Okay, so I said that this was. Why is it not? Well, I still think it is. Why? Oh, you know what? I wasn't even looking at it right. Why is it not? I was wrong. Why is it not a buffer? Because it's a strong acid. See, even I make careless mistakes sometimes. So the hydrochloric and the KCl, it is a salt, and it makes sense, but I forgot about it being a strong acid. Why is this one not? Because that is not the salt of the phosphoric acid. What about this one? Acetate and potassium acetate. It is a weak acid, and it is the potassium salt of that, so that's correct. H2CO3, this one's a little hard to see, but remember that this is going to make the bicarbonate ion, which is HCO3 minus. And so you add the sodium in place of that other hydrogen, and that is definitely a buffer. Okay? Does that make you feel better that I make careless mistakes sometimes too? That's it. That's the end of 8.6. Hopefully you have gotten the hang of this chapter. Make sure that you go back and review any of the sections that you need to before you get ready to try to take that quiz. And there are also some tutorials in this section about how to do some of these calculations. So go on and look at those to make sure, go through those tutorials, because I have some extra problems that I work through for you and that you can do along with me. Alright, thanks for staying tuned.